All right, so like we said, the idea here is that we have a structured course to try and teach everybody the first principles of computational engineering, and to try and get everybody not learning software, but learning the basic fundamentals of what they need to know for their career as a computational engineer. The fundamental aspect of this curriculum is based and rooted in a syllogism, a little bit of a comparison between what engineering is, how we've learned as engineers our craft, and sort of how computer scientists learn. There's a lot of similarities. I think it's important because most people say, I want to be trained in Grasshopper or Dynamo. But when you actually look at things, it's not the way that you're going to get far in life. So for instance, if it was engineering, in engineering we learned some basic math and physics, we learn the sciences, then we learn engineering theory, which is a bit more of applied science, but still science. Then we come to the industry and we learn building codes and software, right?
Yeah.
But you're only as good as how wide the base of your pyramid is, right?
Yeah.
So if you were only knowing, let's say, engineering software, we wouldn't call you an engineer. You wouldn't be a good engineer, let's put it that way. You wouldn't be nearly as good as the guy who knows the full shebang, right? Same thing goes for computer scientists, right? They learn statistics and math. Their base of knowledge is the same. They learn computer science theory, they learn computer languages, and then they learn software, right? So if some people come to me and say, let's do a training course in the software, that really is the problem. That is nice, but you don't really understand what you're doing. And it makes it a lot harder to learn these things because you don't appreciate the underlying rules of what's driving some of what's going on up here.
Great.
Now, computational engineering, to me, is really understanding both of these pyramids very well, right? The higher on each pyramid that you have, you use these pyramids to sort of prop yourself up, right? If you ask me, it's actually more like if you have both pyramids, you don't just, you add them together. Their height gets added together. So you just take both and you stack them on top of each other, right?
Yeah.
So the entire portion of this course is understanding a lot of what goes on down here first. And then, so you get the computer science theory, and then as part of this, you will also get computer languages and software as a natural progression of things, because you'll need it. Now, in here, there's two main things that we need to understand in this order. One is objects, and two is algorithms.
Yeah.
Now, this is the key. People normally come and they say, what can I do with, you just heard him, he said, what can I do with dynamo? And you see practical examples of that. They're talking about algorithms. They're talking about instructions that you can give to the machine and say, do this, 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 and this, because they understand the machine is very good at executing, and it does it better than humans, right? The problem is in order to fully be able to tap that knowledge, even with stuff like Dynamo and Grasshopper, which lower the bar to entry, you need to understand what objects are. Because to speak the language of a machine, the machine always is talking about objects in most of what we talk about in our industry, right? Industry is special in the sense that everything is tangible. You can touch the wall, the ceiling, the floor. So it's really important to understand not only what is the object in engineering terms, what is a facade, what is a door, but also it's just as important to understand what does the computer see. So when you talk about a door, what is it in the machine? Oh, it's the door in Revit. Yeah, but what is it? Can you really understand what that is, right? So that's fittingly why the first chapter is all about objects, because when you talk about what we do, it boils down to stuff that can be described as objects. And now we have to understand, how does the machine see those objects? Because if we understand that, we can then be able to tell the machine, do this, do this, do this, do this. Now, the way this works in general, in practice, is, to break it down to something very simple here, the machine will always take, my pen is, causing me problems. There we go. it always works like this. The machine takes something in,
Something up.
it does some stuff, which we call the algorithm, step 1, step 2, step 3,
Yeah.
and it gives you something out over here. It's as simple as that, right?
Yeah.
And if you start framing everything in terms of, I think of everything as objects, so what goes in is an object, what comes out is an object, which is usually how it is, you start to understand why an algorithm might or might not work. So some of these tools that you get, they might not work if you give them something that they're not expecting, but it's because you don't understand what objects are that they won't work. So there's plenty of stuff out there that's ready for you to use, but if you don't understand objects, it's all lost on you. So one of the key things that we want everybody to walk away from as part of this initial L&D sessions is the ability to do computational engineering on paper. But computational engineering really is just a mindset. It is the idea that you have these two skills and you know how to look at a problem from an engineering perspective and a computer science perspective and think forward to backwards, backwards to forward. Understand, how do I go, and this is what we'll do in this course, how do I go from this to this algorithmically? How can I do that with the machine, right? So that is an appreciation of I got this, I want this. Now how do I describe that going from this pyramid all the way to this pyramid? We always start with good engineering. You can't be doing this side of things in our industry without good engineering theory. So this is all predicated on you're a good engineer in the first place. So this is like the input-output board. On paper, you're literally going to be sitting here, and I would say you start by saying, okay, this is version 1, right? Version 1 is straight up English, Mandarin, whatever language you want to do it in, but it's human. It's completely first principles too. We're not focused on anything other than don't talk about Revit, don't talk about Dynamo, don't talk about the machine, talk about if you were telling me how to do this, what would you say? Step 1, right? Do this. Step 2, do this. Step 3, do this. And after step 3, right?
Yeah.
You get this, right?
Yeah.
So an algorithm that might work in English would say select
The mouse
mouth, right?
and mirror all rotated by 100 degrees.
Rotate 180. Not hard, right?
Yeah.
Not hard when you're saying it in English, right?
Yeah.
Rotate 180 and done,
And
basically.
yeah. Yeah.
You know? So it's not difficult, right? But then when we start to say, okay, let's start moving closer, so that's version 2. Let's start moving closer to, now, let's do it in the machine, right? So now the second part is it's not just that we have these pictures here that we're drawing by hand. It's now that we start throwing on to this picture, what is this? So I'm going to put a box here that says, data-wise, what is this? Now let's say, for instance, this is a DW, right? And let's say, for instance, this is a Revit file, right?
Yeah.
Or
what
it could be a DWG.
Yeah, exactly. Yeah.
Right?
Yeah.
But it makes a huge difference, right? So that's the thing, is what was a very easy off-the-cuff response now is very much dependent on whichever one of these I throw down, right?
Yeah.
And it's completely dependent, and it will have a huge ramification on what happens in here, right? Because if I put Revit here, and you're a Dynamo or Grasshopper guy, right? You're like, uh-oh. Now I automatically know that I need to pipe something over to Dynamo in some way, shape, or form, right? So now the question is how do I select mouth? What does that mean now? To select something in the machine, have the machine select something, right?
Split that face into objects, like a circle, 2 dots. And
Like it's just, for right now, let's take it as rhetorical, right?
Okay.
Is if we're sitting here and saying, listen, if we want to split this space, we need to know, first of all, what is this space? Where does it exist, and what does the computer see? So, and then so that sets off the conversation, because if this was 1 circle, 3 circles in an arc,
Yeah.
the difference of this algorithm to if it was, let's say, 100 lines. Let's say it was 100 lines. It looks like that, but it's 100 lines. Those two algorithms are very different. And also, if the output's this versus DWG versus a PDF, it's all going to be affected, right?
Yeah.
So as you go down, what we're hoping is everybody always starts on paper, and effectively, you go through a few iterations on paper where effectively you go from English to pseudocode to nearly code, right? So you start to, on paper, sort of appreciate, okay, well, this was my original idea, but this is my idea, this is my original idea from only this side. But now, if I start to consider a bit of this over here, it changes the paradigm here, right? And if I consider it more and more and more, maybe there's a bit of a feedback loop going on here, right? So this is the engineering feedback loop mixed with the computational science. The more you get involved on this side, the more this might need to change. But eventually what you end up with at the base here will be the algorithm that actually allows you to do stuff useful that is empathetic with the engineering, but also empathetic with the machine. This is what it's about, having the empathy with the machine such that you can actually tell the machine how to do your job, the parts of the job that are repetitive, mundane, visualization based, and also just stuff that's meant to be done by a machine, like remembering stuff, right? So that is the main thing that we need to see everybody doing, because if you're not starting on paper, it's extremely easy to get lost, especially when you're starting, right? Because there's a lot of stuff to learn here, just that the stuff that we'll go over, right? The introduction to Grasshopper, the introduction to Dynamo, all that other stuff. Now, if you list it out like this, you can't go on the internet, right, and type in. There's plenty of resources, but you can't type in how to make my frowny face smile. What you can do is say, how do I select one curve out of many, right?
Yeah.
How do I rotate one curve in Grasshopper, right? So effectively, by doing this, not only are you learning the approach of a computational engineer very well, and keeping things from first principles, but you're also making the learning process much easier, because instead of having it be this big thing, this big problem to solve, which you'll see, you could make this problem very complicated to go from here to here. If you break it down like this, effectively what you're doing is you're creating for yourself a bunch of mini lessons, right?
Yeah.
So as part of this course, chapter 1, there's 3 chapters. Each chapter has 10 files. All of the files will look the same to you. They will all start with a frowning face. But to the machine, especially chapter 1, the machine sees something different every time. So what your challenge is going to be is, great, for all of the 10 files, your version 1 of the script on paper from first principles isn't going to change, because we're not changing this paradigm here. What will change is this, right? The DWG aspect of things, or actually what the data is, not what it looks like. It will always look the same to you, but it will be different in every situation, which will have a knock-on implication on your algorithm, right? And that's the big thing, is once you have this skill down, these will get more and more complicated, the 10 files, and more, what you'll see is it's very important to know what you're going to do before you go to the machine, from first principles, engineering, and computer science. Because then you can start, once you understand, remember, all this iteration is really just the iteration of kind of a little bit of iteration in there between first principles engineering and computer science. Eventually, you'll elevate that to talking specifically about, okay, I want to do a rotation of 180 degrees in Grasshopper, let's say. That's very specific now. That's one line item that you now need to learn, which is very easy to teach. It's not easy to just, and it's not fun to sit here and go through this example. No one's going to go through, as part of this, 10 files and show you exactly how to do them. It's dumb, because you won't learn that way. What we want to teach is the meta skills that you need to be a computational engineer, which is, first of all, doing stuff like this on paper, understanding both pyramids, and then also understanding where to find the answers, right? Teaching a man how to fish rather than just giving him the fish.
Yeah.
So that's what this is all about. So between this first chapter, really, everybody's tempted to just jump right into Grasshopper. And we will give a quick introduction to sort of the user interface normally. I mean, I know you got a lot of it down, but normally what we'll do is you'll be forced as part of this first chapter to use Dynamo and Grasshopper. You don't have to, but it's highly encouraged. After that, you can do whatever you want. But the key here is in both of those, you need to have a bit of a upskilling session on just sort of the user interface, how things work, the components. Like, you're not trying to teach Grasshopper. We're trying to teach how to figure out Grasshopper. Because to teach Grasshopper or Dynamo is stupid. Because at the end of the day, you can't ever learn all of the components. Like, I've used it for 7 years, and I still don't know the components. And there are always new components coming out. So to teach the actual software is a fool's errand. To teach the underlying skills of using the software can actually get you into the space much more effectively. So that's it. What does the computer see? Every time in this lessons, the entire first 10 files are completely based off of, you will see the same thing every time. The machine will see something different, and it will be diabolical at times, the differences, and it will completely every time screw up your algorithm from before. It's been engineered that way. So do not expect to make one script to solve them all. Get the problem in, solve it on paper with the specific criteria you have. So that, for you especially, be careful. Do not try and solve all 30 files one script, because it won't work. Because it's been engineered to not work that way. You'll eventually have, what we really want to see at the end of all this is that you take step 1, 2, and 3, for instance. Let's say there was 1, 2, 3 at the end of this. So let's say your script says at the very end of this it's 1, 2, and 3, right?
Yeah.
Okay. So what we want to see, and you've seen the way that, we're really recommending to script now, is if it were Grasshopper or Dynamo, we want to see step 1, right? And there's a group, and there's an input here, and it goes in, and it does some jazz, right? And out comes something else, right?
Yeah.
And then you got step 2, same thing, just do 1, and then step 3, same thing. So that there's actually English, so you've basically taken these, you've embedded them into the code, so now your logic is clearly stated to everybody else, and also it's modular in the sense that if this doesn't work out, so if it ends up being that you've realized actually it's not going to work this way, you can just take that out and replace it with something else, so it's modular, right? But that's the other big thing is if you're already in thinking this way from day one in terms of step 1, 2, 3, it's very easy to start making things very clean 1, 2, 3. And for the purposes of this course, what it'll mean is at the end of chapter 1, you'll have hopefully a Grasshopper or Dynamo file with 10 scripts, all of which will be sort of looking just like this, right? So each one of these guys right here will be one of these. And you'll have 10 different algorithms that you've written, and you'll have 10 different skill sets that you learned.
So question, so for the 10 files, seems like it's 10 tasks, right? So are they related to each other, or they're like separate ones?
They are related in the sense that
in the order,
they
right?
will all, in theory,
Okay.
you will be able to say, this is the algorithm for all of them.
Yeah.
Right? You'll be able to say, hey, actually, from first principles, it's a frowning face that needs to be smiling. That's not changing. The first principles of the problem, it's the same task on all of them. What's different is you have 10 files that are all slightly different, despite the fact that to your face, they look exactly the same. Okay?
Okay.
So that's it. That's the introduction. That's chapter 1. If you do chapter 1, you will have the meta computational engineering skills that you need to go on to chapter 2 and 3. If you do chapter 1, 2, and 3, then I think you have the fundamental tool package at the base of this pyramid to be able to really start talking about higher level interaction between this computational engineering, which is the sort of mixture of, in your engineering mind, having these skills in your brain, which allows you to be a computational engineer, which allows you to understand, hey, there's certain things that I have to do with my hands, but there's also certain things that the machine should be doing, which is extremely valuable. But it all is predicated on, first of all, understanding some empathy with the machine. What does he see? So these first 10 exercises, I think, are a very good example of it.